Hello everyone, welcome to our channel. So let's get started. So in this video we will solve one more question asked in the previous GATE exam. So hope this series will be helpful to cover all fundamentals of control systems. Okay, so all right. So here let me state the question. So the unity feedback system that uses proportional integral control system shown in figure. Okay, so here the proportional integral controller, okay, generally called the PI controller. So in the figure, generally we can understand that they given the controller Kp plus Ki by S. So there are two variables Kp and Ki, and this is my plant or process. Okay, so in this for which we want to design the controller. So this transfer function assistant generally we call the plant and process. Okay, so here they're saying that the stability for overall system is controlled by tuning the PI control parameters Kp and Ki. Okay, because we want to stabilize the your system. Okay, so that's a responsibility, we can say responsibility of the controller to maintain the system stability, plant stability, and with achieving the all performance requirements like rise time, certain time, bandwidth, like that. Okay, and maximum value of Ki, and they are telling that what is the integral Ki value that can be chosen so that keep the overall system should be stable, or if the brush can be can say at the verge of stable, we call that marginal stable. Okay, so we need to find out the Ki value. Okay, maximum Ki value we need to find out here. So all right, so how to solve this? So first we need to, what the step? First we need to develop and establish the Curtis equations, and because here they are telling about they are talking about the stability, so we need to apply the Routh-Hurwitz criteria so that we should understand what's the range of Kp and Ki for which our Ki value would be maximum to maintain the stability. Okay, so what's the useful data to required for to solve the this question? Okay, so as we know, in case of stability, we need to apply the Routh-Hurwitz criteria. So as we know, the necessary condition for Routh-Hurwitz criteria like coefficient of characteristic polynomial should be positive. Okay, so once we like our here you can see like this my plant GS, generally we call the, like for this we just take it P. Okay, like this my PA, this my plant. Okay, and for this take it this my controller CS transfer function, this my reference RS, and this my feedback. Let's take general block diagram GS, sorry HS. Okay, this my output by S. So so what is our closed loop transfer function? Ys by Rs. Okay, so for this we know the our fundamental block diagram, like this is a GS. Okay, and this is our HS plus minus. So in case of control system, for stability point of view, we take the our negative feedback system. All right, take this by S. So here by S by Rs equal to GS by 1 plus GS into HS. Okay. So here GS is equal to, for our given question, GS is equal to CS into transfer function of control system controller into plant transfer function PS. Okay. And here, since this is a unity feedback system, so HS is equal to 1. All right. So hope you understood. So here, what is a characteristic equation? Characteristic equation would be, yeah, characteristic polynomial 1 plus GS into HS. This by characteristic polynomial. Let us say CHAR and put yes. Okay, characteristic equations polynomial. Sorry. So 1 plus GS into HS. Here we can say 1 plus what is the GS? GS equal to CS into PS for our given question. CS into PS into, alright, into HS. So HS since it is 1, so there is no meaning to write here. So sufficient condition for Routh-Hurwitz stability. All the elements of first column of Routh array should be in same sign. So once we form the Routh-Hurwitz table, so first column is important to ensure that whether given system, given plant is stable or not. So well, this should not be any sign changes. If a number some sign changes occur, then it will ensure that our system, given system is unstable. Okay. So let us first solve the establish our Curtis equation. So for this, our closed loop transfer function Ts CLTF closed transfer function equal to GS by, since this is our negative feedback system, that's why we consider plus. A positive feedback, we consider the minus here. Okay. So GS by 1 plus GS HS. Okay. So is positive for negative feedback, and if you have the positive feedback, then it will be negative sign. Or better, here you can see positive sign for negative feedback. Let us write here. Okay. And negative sign for positive feedback. Okay. So here GS will be, for our given question, GS is PS into CS. Okay. So what is a PS actually? Plant transfer function 2 by s cube plus 4s square plus 5s plus 2. 2 by s cube plus 4s square plus 5s plus 2 into our controller. Controller will be Kp plus Ki by S. Okay, so let's simplify. 2i by s cube plus 4 square plus 5s plus 2 into Kp Kps plus Ki by S. Alright. So here 2 Kp S plus Ki y, yes, you can multiply complete equation. So it will be turned out in order 4. s power 4 4s cube plus 5s square plus 2s. All right. So what would be our CLTF closed loop transfer function? Ts equal to gs by 1 plus gs, since hs is equal to, here for given question is 1. Okay. Let us write here. So CL TF equal to gs by 1 plus gs. So it will be 2 into kps plus ki. Y s power 4 plus 4 into 4sq, right, plus 5s square plus 2 into s. Okay. Okay. All right. So then hold 1 plus so here will be 2 into kp into s plus ki divided by s power 4 plus 4s cube plus 5s square plus 2s. Let us simplify. So 2 kps plus ki. Okay, this denominator part you can take it like this one, assume like a, otherwise no need to assume, no problem. Okay, keep like that only. Divide by, complete divide by s power 4 plus 4s cube plus 5s square plus 2s. Okay, so here coming, just take simplify s power 4 plus 4s cube plus 5s square plus 2s into 2 kp into s plus 2 ki. Okay, and whole divided by this same term, s power 4 plus 4s cube plus 5s square plus 2s. Okay, so here you can see this term cancel out, so remaining would be 2 into kps plus ki y s power 4 plus 4s cube 5s square 2s. This term is same, so just let us collect this term, same term, plus 2 plus 2 kp. Okay na, and s, and remaining our constant term 2 ki. Okay, so this our final transfer function, and our denominator polynomial would be our characteristic polynomial. All right, characteristic polynomial. Okay, so here we need to apply the Routh-Hurwitz criterion. So we can say our necessary condition would be all signs should be same. So here you can say all sign is a positive. So we can say this is our variable term. So 2 plus 2kp greater than 0. So it turns out kp value less than minus 1. Sorry, greater than minus 1. Alright. So it turns out to be kp greater than minus 1. So this is one condition. Okay. And then this our constant on 2ki. This also must be greater than 0. So this also turns out to be ki greater than 0. Alright. Okay. So let us form our Routh-Hurwitz criteria. Then only we can table. Let us form the Routh-Hurwitz table. So what is our characteristic polynomial? So 4s power 4 plus, sorry, so this is not 4, so it will be s power 4 plus 4s cube plus 5s square plus 2 plus 2kp into s plus 2ki. Alright. So here this is our order 4. So s power 4, s power q, s power 2, s power 1, s power 0. I'm forming the Routh-Hurwitz table. So s power 4, take the s power 4, this term and this term. Okay. So this will be constant 1 and this is a 5 and 2ki, and this is a remaining 4 and 2 plus 2kp. Alright. Then we need to fill remaining row. So how to fill it? Just multiply like 4 into 5 minus 1 into 2 plus 2kpy and divide by 4. So here 4 into 5 minus 2 plus 2kp divided by 4. Let us solve it. So 20 minus 2, 18 minus 2kp by 4. Let us again solve 9 by kp by 2. Let us say this term is a. So this term is a. And just stretching this and then solve it. Similar. So here term is not there, term 0. So 4 into 2ki. So this is 4 into 2ki minus this 1 into 0. So by 4. So again is coming 2ki. Okay na? Okay. Hope you understood. Then so again let us this multiply a into this one minus this divided by a. So a into 2 plus 2kp minus 4 into 2ki. So 8ki divided by a. So it will be a into 2 plus 2kp minus 8ki. by A. Yeah, we can say this complete term we can assume like a B. So it will be maintain the here cleanness. So B, otherwise it looks clumsy. Okay, so it will be, and this will be term 0. So remaining term is a 2ki here. Okay, so our sufficient condition would be in Routh-Hurwitz table, this first column, right? All there should be no sign changes. Okay, so for in order to maintain all sign change, all sign is same, then A and B also greater than 0, like 1 and 4, 2ki already positive. So we can say A greater than 0, B greater than 0, 2ki greater than 0. It means this thing we already seen in necessary condition, ki less than, oh, sorry, greater than 0. So this thing we need to take care. A greater than 0 and B greater than 0. So let us take care A. What is A here? So A would be, A value is 9 minus kp by 2. 9 minus kp by 2 greater than 0. So kp 9 greater than 0, kp less than 9. So here you can see in our necessary condition we already established the kp greater than minus 1. Alright, and sufficient condition for Routh-Hurwitz table we established the here kp less than 9. Okay, so our range kp would be minus greater than 1 and less than 9. Okay, hope you understood. And take b value. So b also greater than 0 here. So what is the b value here? B value is A into 2 plus 2 kp minus 8 ki. So A into 2 plus 2 kp minus 8 ki ya greater than 0. Okay, so here you can see A 2 plus 2 kp minus 8 ki greater than 0. So what is the A value? A value is 9 plus kp by 2 into, you can take 2 common, 1 plus kp minus 8 ki greater than 0. 2 to cancel out. So remaining is 9 plus kp 1 plus kp minus 8 ki greater than 0. So here usually you can see, here in this equation we need to find out the ki, right? So what is the ki here? Ki would be less than 1 by 8 A value is A value is 9, not plus kp, is minus kp, right? So 9 minus kp, so it will be minus kp. Okay, so it will be 9 minus kp into 1 plus kp Okay, so let us solve this. So ki is a function of kp, okay, which is a quadratic equation, right? So what is a 1 by kp? So here 9 plus 9 kp minus kp square. Okay, so finally ki less than a 1 by 8. So 9 plus 8 kp minus kp square. Okay, so you know like this your function where ki depend upon the kp, which is quadratic equation. So ki is a function of kp. All right, so for this ki should be maximum, then it only possible when derivative of ki with respect to the kp, or we can say function of kp is equal to 0 and double derivative, right, is less than 0. Then only we can say our ki value would be maximum. Okay, so here, so what is our dki by dkp equal to, this is a 0 plus 8 minus 2 kp is equal to 0, kp is equal to 4. Okay, and what is the double derivative? It should be negative, right? So it should be minus 2, so it is less than 0. So this implies that at kp, k is equal to p, for this our value ki value will be maximum. Okay, so what is a ki maximum value? You can see here ki less than 1 by 8, 9 plus 8 into 4 minus 4 square. Okay, so ki less than 1 by 8, 9 plus 3 2 minus 16. So ki less than 1 by 8, this will be coming out 9 plus 16. Okay, finally 25 by 8. So our ki value should be, range would be, like let us solve 25 is coming 3.8 3 ja 24, 1 0, 8 1 ja 2 12, sorry 20, 8 2 ja 4 40, 8 5 ja. So our ki value would be, maximum value coming is 3.125, otherwise less than that. Okay, because they are asking about maximum value, so it will be 3.125. So you can also draw in a graph, like it will be give better overview, better understanding, like this my kp. So kp range would be minus 1 to plus 9, because this is a quadratic equation, so ki always greater than 0. So minus 1 and 9, this means ki always 0. I'll just draw the typically raw diagram. Okay, let us correct, let us draw again. Okay, so here this value will be maximum at kp value is equal to 4. So this value is 3.125, or we can say 25 by 8. Okay, so for our given question, ki maximum value would be 3 decimal, right? They are asking. So ki value is 3.125. Okay, so that's the answer. Correct answer. So all right. So this question covers your fundamentals or Routh-Hurwitz table, Routh-Hurwitz criteria like necessary condition and sufficient condition, and also is extend the your concept like how to find out the maximum value. Okay. So this given question they converted ki function in terms of the kp function. Okay. So for this maximum value we need to apply maximum like derivative, and so if you don't find out the what's the value of kp, our ki would achieve the maximum value. All right. So that's the question. Hope you understood. So that's all. Thanks a lot.